Hello, everyone, and welcome. Today, I would like to talk about binary search tree iterator. This question basically asks you to implement two functions. First, the Boolean hasNext function. Second, the integer next function. They are actually pretty straightforward. But the key question here is the follow-up. Could you implement next and hasNext to run in average O1 time complexity and use OH memory, where H is the height of the tree? So how can we do that? First of all, I'd like to show you when we will exceed the space complexity of OH. So if you are familiar with the in-order traversal based on recursion, you know it can be implemented like this. And feel free to look up my other video about binary tree in-order traversal in more details. And based on this implementation, the next function and hasNext function is pretty straightforward. And they certainly has a O1 time complexity as required. However, because you use the resource array to store the whole in-order traversal, so this has a space complexity of On exceeding the requirement of OH. So how can we achieve space complexity OH without storing the whole in-order traversal? Well, the problem with recursion is that it's harder to exit out this recursion once it's started. So instead, let's try iteration to see if it's easier to exit out the iterative loop as needed. Here's an implementation of in-order traversal based on iteration. If you are not familiar with this implementation, please feel free to look at my other video about binary tree in-order traversal in my channel. So as you can see, the in-order traversal based on iteration kind of mirror the implementation in recursion. However, the most important distinction here is that we are using a while true loop, and certainly it's a lot easier to exit out the iterative loop. And if we look into this implementation a little bit closer, you can see this part is the left subtree traversal part. It goes through from the root node all the way to the leftmost leaf node. It certainly has the maximum depth for the stack in terms of the height of the binary search tree. So as long as we keep the maximum depth of the stack array to be within H, then we can achieve the space complexity of OH. More specifically, to achieve space complexity of OH, do not store the full in-order traversal in the resource array. Rather, leverage the stack, which has the maximum depth of OH, to store the process of the in-order traversal, and then use the stack to implement next function and hasNext function. With all the background introduced, now let's write the code. First of all, we want to remind ourselves the code from iteration-based in-order traversal, because we're going to leverage the code to build our BST iterator here. So the code has this while true loop if current is not known, then we will append that current node to the end of the stack or at the top of the stack. and then have the current point to the left child node. And this way, we build the left the left subtree and store in stack. Okay, and at the end of the left subtree, we reach terminal leaf node. Then we have this else if the stack. We start to process the top item from the stack. We have this pot operation here to return the top item from the stack, and this is similar to the next. And we want to append that value of the node into the resource array, and this is important to the next. And then finally, importantly, we have this current point to the right child node to continue to build the left subtree from the right child node and store it in stack. So this is what it's doing here. And then finally, if we have no like the stack is running out, we break. So this is similar to hasNext. Okay. So now let's declare a variable, a self variable, the self stack, so we can use it in this class across different functions. So self stack is empty array. And then, first of all, we're going to implement this part to build the left subtree and store in stack as a function. So define in order traversal left subtree self current with current to be consistent here, and while current, so it's important we condense these two code here, while true and if current, while current, we simply stack, we simply append that node in the stack and then have current point to its left child node. Okay, so this way we can build the left tree and store in stack. And we want to build that initial left tree, so we call the Inorder left subtree and loop node. So to build the initial subtree here, okay. And then how about this next function? So this next function, as we mentioned, it will be leveraging this part here. So we always assuming there's a next available, so we don't need to do if stack. Whether the current will be the last item. So we use a pop method here, and then we want to just return the value as in here. But before we do that, there's also this part current point to the right child node, and to continue to build the left subtree and store in the stack from there. We need to have that part in the next as well before we return. So to do that, we simply call the Inorder left subtree function using current dot right. So this way we can continue to build the left subtree from the right child node if it's available and store in stack. So if this current dot right is none, it's not going to be processed because it has this while current here. And finally, we will implement this hasNext. Well, hasNext is similar to this if stack. So we simply will test the length of the stack. If it's greater than 0, it means it has next, and continue to be, we can continue to process this. Okay, so and that's the code for this BST iterator. Okay, so now first of all, let's test this code to see how it works. So we submit and done. So yes, it passed both the requirement for the time and the space complexity here. It's pretty good. Now we'll analyze the code for complexity. Since we designed the code with space complexity in mind, we know our space complexity is certainly OH, since the stack has maximum depth of H, and H is the height of the tree. And for time complexity, the question asks O1 on average. So let's see if it has O1 on average. So for hasNext, it's not just on average, it's O1 every time. And for the next function, is the pop and return, that's O1 on every call. But for this calling this function here is a critical part, so we analyze it. This part has amortized O1 time complexity, so it's still meeting the requirement on average. It's just not every call, but on average is O1. It's because the worst case is n from current the right channel is ON, very skewed binary search tree, but most of the time is either none or just one right channel. So it wears off that possibility by this none or just one channel. So amortize to be O1. Alright, so that's all for this video. Hope you find this video to be useful. Please stay tuned and subscribe for more videos. Hope to see you next time, and goodbye.